Hello, my dear friends. How are you? Hope you're fine. What about your studies? Study well. Keep going, study. Okay, today we are continuing the fifth chapter, that is surface chemistry from catalysis onwards. Okay, that is catalysis onwards. Okay, without wasting time, we can directly go to the chapter. Okay, let first is catalysis. What is catalysis? Do you studied about catalysis? Yes, we know that what is catalysis and what are the uses. So, what is catalysis? Yes, that is increase the speed of a reaction, rate of reaction. Okay, that is substances which alter the rate of a chemical reaction and themselves remain chemically and quantitatively unchanged after the reaction are known as catalyst. Okay, that is a catalyst only what that is only enhance the reaction without losing or without gaining anything. So catalyst itself did not gain anything. What did it do? His function is only to faster, to increase the rate, enhance the rate. Okay, once again, substances which alter the rate of a chemical reaction and what are their properties and themselves remain chemically and quantitatively unchanged. Chemically and quantitative, that is after the reaction the platinum or any catalyst that is used in cannot undergo any change and its amount cannot be reduced or increased. Okay, if you take 1 gram for the reaction, after the reaction you get the 1 gram, so no change in the amount. Okay, that is no change chemically and quantitatively. Okay, that is about catalyst. What is promoters and poisons? What is promoters? What promote? Promoters are the substance that enhance the activity of a catalyst. Okay, promoters are the substance that enhance the activity of a catalyst. So it is a supporter or a supporting for whom? For the catalyst, or a supporter of a catalyst. Okay, that is promoters are the substance that enhance the activity of a catalyst. What is poisons? What is poisons? Yes, it is a reverse of promoters. Promoters decrease the activity of a catalyst. Okay, promoters decrease the activity of a catalyst. Got the point? Okay, then we can move to homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis and heterogeneous catalysis. What is meant by homogeneous? That we have studied in the first chapter in +1 chemistry. What is homogeneous? Yes. Here, homogeneous catalysis means the reactant and the catalyst are in the same phase. That is, if reactant and the catalyst are the if solid, it is homogeneous catalysis. If reactant and catalyst are liquid, it is homogeneous catalysis. And if the reactant and the catalyst are in gaseous phase, then it is homogeneous catalysis. Okay, that is the reactant and the catalyst are in the same phase. It is the homogeneous catalysis. Got the point? Okay, if we take an example, SO2 sulfur dioxide is converted into SO3 sulfur trioxide using nitrogen into as catalyst. Okay, what is the case? Here sulfur dioxide, oxygen, nitrogen, all three are in gaseous. Okay, then what we can say? It is an example of homogeneous catalysis. It is an example of homogeneous catalysis. Okay, next we can consider another example, hydrolysis of methyl acetate with HCl, hydrochloric acid. Hydrolysis of methyl acetate with hydrochloric acid. Here, what? Methyl acetate, HCl are in liquid state. Okay, then it is also an example of homogeneous catalysis. Got the point? What is homogeneous catalysis? When the reactant and the catalyst are in the same phase. Okay, that is called a homogeneous catalysis. Okay, I think it was clear. Then we can move to heterogeneous catalysis. That is this opposite of homogeneous. What is? Yes, the reactant. When the reactant and the product, when the reactant and the catalyst are in different phases. When the reactant and the catalyst are in different phases, it leads to the formation of heterogeneous catalysis. Okay, then we can take the previous example as conversion of sulfur dioxide to sulfur trioxide SO2 to SO3 using platinum as catalyst. It is an example of heterogeneous catalysis. What is the case? Yes, here SO2 is in gaseous form whereas platinum is in solid phase. Then it is an example of catalysis of heterogeneous type. Okay, then we can go another example, it is in the preparation of ammonia Haber process. What is the case? In Haber process, using catalyst is iron. Iron is using as catalyst. So the reactant is in gaseous form and the catalyst in solid form. What will happen? Yes, it is an example of heterogeneous catalysis. Got the point? Okay, we can move to another important topic, that is adsorption theory of heterogeneous catalysis. That is heterogeneous in the theory behind the heterogeneous catalysis. Okay, this theory explains the mechanism of heterogeneous catalysis. Adsorption theory explains the mechanism of heterogeneous catalysis. Okay, this adsorption theory is a combination of modern adsorption theory and intermediate compound formation theory. That is, this theory is based on the intermediate compound formation. It is the modern adsorption theory combination of intermediate compound formation theory and old adsorption theory. Okay, that is, this theory is the combination of intermediate compound formation theory and the old adsorption theory. Okay, the activity of a catalyst. The activity of a catalyst is localized on the surface of catalyst. Okay, that is, the activity or the efficiency of a catalyst is dependent on the surface of catalyst. Okay, so the main points, the main assumptions or the main statements in theory can be studied. So we can take one by one. Okay, the first one is that diffusion of reactant to the surface of the catalyst. That is, diffusion of reactant to the surface of the catalyst. So the first step, the reactant molecules come close to the surface of the catalyst. Okay, and the second step, adsorption of the reactant molecules on the surface of the catalyst. And the second step is the adsorption of reactant molecules to the surface of the catalyst. And third step, this is the important step, that is, an intermediate is formed on the catalyst surface and a chemical reaction occurs. That is, in the third step, the chemical reaction occurs by the formation of an intermediate. Got the point? That is, in the third step, an intermediate is formed and a chemical reaction occurs. Okay, and the fourth statement, desorption of the reaction products from the catalyst surface. Desorption of the reactant products from the catalyst surface. Okay, and what will happen? Thereby making the surface available again for more reactions. That is, desorption of the reaction product from the catalyst surface, and the catalyst surface is again now available for more reaction. Okay, and the fifth point, diffusion of reaction products away from the catalyst. Okay, diffusion of reaction products away from the catalyst. Okay, so we have already discussed that the surface of adsorbent, in the case over here it is catalyst. The surface of the catalyst, unlike the inner part, when comparing the surface and inner part, the surface have what? Free valencies. Okay, so these valencies or vacancies provide the seat or the space for the reactant molecules and helps for the reaction. So this force of attraction between the surface and the catalyst is the reason behind adsorption. Okay, we can go to the next point, that is, if different reactant molecules are adsorbed side by side in the catalyst, they may react with each other. What will happen? Yes, resulting in the formation of new molecules. Okay, different molecules adsorb side by side, there is a chance of reacting with each other for the formation of new molecules. Then what will happen? The formed molecules may evaporate from the surface. Then what will happen? Yes, the surface is available for the new reactant molecules. Got the point? And these 5 to 6 points are the main postulates of this adsorption theory, and this theory is a combination of intermediate compound formation theory and the old adsorption theory, and the main points we discussed. So you may study these points, it is very important. So next we can discuss about the merit of this theory, how this theory is applicable. This theory explains why we need a small amount of catalyst and why the catalysis remain unchanged in the mass and chemical composition. This theory explains why a catalyst remain unchanged in quantity and mass, quantity and quality after the reaction, and why a small amount of catalyst is enough or effective. These two questions can be easily explained with this adsorption theory. There is a very small drawback is that it could not explain the catalytic properties of promoters and poisons. Okay, it failed to explain the catalytic properties of promoters and poisons. Okay, next we can check the important features of solid catalyst. Important features of solid catalyst. The first one is activity. What is activity? Activity of a catalyst depends upon the strength of chemisorption. Activity of a catalyst depends upon the strength of chemisorption. What does it mean? Yes, the reactant must get adsorbed strongly on the catalyst surface. That is, when a reactant to become active for the reaction, the reactant must adsorb strongly on the catalyst. Okay, and this force should not be very strong, because after the reaction it need to be replaced. Okay, that is, they must not get adsorbed so strongly. They are immobilized because they needed to remove from the surface. The catalytic activity increases from group 5 to group 11. In the periodic table, from the group 5 to group 11, the catalytic activity increases. And maximum activity is being shown by group elements of group 7 to 9. In the periodic table, the catalytic activity increases from group 5 to 11 and the maximum activity being shown by elements of group 7 to 9. Okay. Next we can study an important feature of solid catalyst is selectivity. What is selectivity? Yes, that is selective path. What does it mean? The selectivity of a catalyst is its ability to direct a reaction to yield a particular product. That is simply, if we use one kind of catalyst, it will give one product. If we use another catalyst, it will give another product. That is the case of selectivity. To direct a reaction to yield a particular product is the case of selectivity. Okay, we know that the reaction of carbon monoxide with hydrogen gives methane, methanol, formaldehyde. These all products can be obtained from the reaction of carbon monoxide and hydrogen. How? That is by differing the catalyst. If we use nickel as catalyst, the reaction will give methane. That is, carbon monoxide with hydrogen gives methane if nickel is the catalyst. Okay, carbon monoxide and hydrogen gives HCHO, formaldehyde, if copper is the catalyst. And carbon monoxide and hydrogen gives methanol when if the catalyst is copper, zinc oxide, chromium oxide as catalyst. That is a mixture. Cr, zinc oxide, copper, zinc oxide, chromium oxide as catalyst. That is chromate. Okay. Next, we can study shape selective catalysis. That is shape selective catalysis. What does it mean, shape selective catalysis? Okay, we can discuss. A catalytic reaction that depends upon the pore structure of a catalyst, size of the reactant, size of the product, molecules is called a shape selective catalyst or shape selective catalysis. Catalytic reaction depend on the pore structure of the catalyst, size of the reactant, product, molecules is called a shape selective catalyst. For example, zeolite. And zeolite have a honeycomb structure. What is its properties? Yes, zeolite is microporous aluminosilicates. Zeolite is a microporous aluminosilicates. And what is its three-dimensional structure? It have a three-dimensional network of silicate. Okay, it have a three-dimensional network of silicates. And some silicon atoms are replaced by aluminium atom. Gives, and what is its framework? Aluminium, oxygen, silicon, aluminium, oxygen, silicon framework. Okay, which have a three-dimensional arrangement. And the reaction of zeolite is mainly depend on three factors. That is, we have already discussed it. That is, this zeolite also depend on mainly three factors: size and shape of reactant molecules used, size and shape of product molecules to be formed, and also depend on the pore structure of the cavity of zeolite. Pores and cavity of zeolite. Okay, and zeolite can be seen in the nature, and it is used and it is synthesized for the industrial purpose. It can be seen in the nature and it is also synthesized for the commercial use. One of the applications of zeolite is that it is mainly used in petrochemical industry. Zeolite is mainly used in petrochemical industry as a catalyst. An example is that ZSM5. An example of zeolite is that ZSM5. Okay, what is its use? It is used in the conversion of alcohol to gasoline. Application of zeolite is that it is used in the petrochemical industry, and an example of zeolite is ZSM5, and ZSM5 is used for the conversion of alcohol to gasoline. Okay, now we are going to the next point, that is enzyme catalysis. What is enzyme catalysis? Yes, like the catalyst, the enzyme is also a catalyst. So we can discuss what is enzyme and what is the properties of enzyme catalysis. Okay, the enzymes are produced by living plants and animals. Okay, the catalyst is simply a metallurgy, like that. What is enzyme is produced by living plants and animals. Okay, what are enzymes? These are complex nitrogenous organic compounds. Okay, these are nitrogenous organic compounds. And the next point is that these are very effective catalysts. Enzymes are very effective in catalysis. Okay, where did they act? Where the reaction of enzyme can be seen where? Yes, reactions that occur in animals. Reactions that occur in animals and plants. To maintain the life process are catalyzed by the enzymes. Reactions that occur in animals and plants to maintain the life process are catalyzed by enzymes. Okay, because of its duty in living and cells, these catalysts are also called as biochemical catalysts. These enzymes are also called biochemical catalyst, and this process is called biochemical catalysis. Biochemical catalysis, the reactions in which an enzyme is used, or the reactions catalyzed by an enzyme, is called an biochemical catalysis. Okay, did we can check some example? That is glucose to ethyl alcohol. The enzyme zymase convert glucose to ethyl alcohol, and the invertase convert cane sugar to glucose and fructose, and diastase convert starch into maltose, and pepsin convert protein to peptide, and conversion of milk into curd. And these are also some examples of enzyme catalysis reaction. Okay, these all are enzyme catalysis reaction, and it is occurring in living plants and animals. Got the point? It is very important that they are very effective catalyst. As comparing with the catalyst, enzymes are very effective in catalysis. Okay. Next, we can discuss the characteristics of enzyme catalysis. What are the characteristics of enzyme catalysis? The first point is that they are highly efficient. Enzyme catalysis is highly efficient. That is, one molecule of enzyme is enough for 1 million of reactant molecules. That is highly efficient. One molecule of enzyme is enough for 1 million of reactant molecule. The next property is that it is highly specific in nature. Enzyme is highly specific in nature. What does it mean? Yes, one catalyst do one type of duty. That is, one catalyst cannot catalyze more than one reaction. If we consider the case of urease, it can do a duty of conversion of urea hydrolysis. Okay, that is one. If you take one catalyst, it will do only one catalytic action. Okay, and the next point is that it is highly active under an optimum temperature. If we increase the temperature to a higher value or decrease the temperature to a lower value, the activity of enzyme will decrease. That is, the enzyme will highly active, or the peak work or the peak activity of an enzyme can seen only under an optimum temperature. Can be seen only at a particular temperature, and this temperature is the optimum temperature. Okay, that is, the temperature at which the rate of an enzyme reaction become maximum is the optimum temperature. Okay, the temperature at which the rate of an enzyme reaction become maximum is the optimum temperature. Okay, and the optimum temperature of an enzyme is usually in between 298 to 310 Kelvin. Usually the optimum temperature is in between 298 to 310 Kelvin. Okay, for human body, enzyme reaction optimum temperature is 310 Kelvin. Okay, for human body, the enzyme reaction optimum temperature is 310 Kelvin. Okay, and the next point is that the enzyme is highly active under an optimum pH. That is, the enzyme is highly active under an optimum pH. What is an optimum pH? The pH at which the enzyme reaction is maximum is called an optimum pH. The pH at which the enzyme reaction is maximum is called optimum pH. The optimum pH is usually found in the range of 5 to 7. The optimum pH is usually found in the range of 5 to 7. And the next point is that in the case of enzyme, the enzyme activity is increases in the presence of activators and coenzymes. The activity of an enzyme increases in the presence of activators and coenzymes. That is, it is observed that when a small non-protein is present along with an enzyme, the catalytic activity enhanced. The catalytic activity is enhanced in the presence of non-protein. Okay, and activators are generally metal ions. Activators are generally metal ions such as sodium ion, manganese ion, cobalt ion, copper ion, etc. And what will happen? These ions, when weakly bound to an enzyme, it will increase the catalytic activity of an enzyme. When an activator is weakly bound to an enzyme, it will increase the catalytic activity of the enzyme. For example, amylase in presence of sodium ions are very active catalyst. Amylase in presence of sodium ions are very effective, very active catalyst. Got the point? Then the next point is that influence of inhibitors and poisons. Influence of inhibitors and poisons. What is its role? Inhibitors or poisons interact with the active functional group on the enzyme surface. Inhibitors or poisons interact with the active functional group on the enzyme surface. And what will happen? And completely destroy the catalytic activity of the enzyme. That is, on the other side, or the what we can say, the activators and coenzymes increase the rate of increase the activity of an enzyme, whereas poisons, inhibitors are completely destroying the enzyme. Okay, or decreases the activity of an enzyme. These are the speciality or the characteristics or the properties of enzyme catalysis That's very important as exam point of view. You must study well. These are characteristics of enzyme catalysis. What is the case of efficiency, specificity, optimum temperature, optimum pH, and influence of activators and coenzymes, and influence of inhibitors and poisons. Okay, next we can discuss the mechanism of an enzyme catalysis. What is the mechanism of an enzyme catalysis? How an enzyme participate in a reaction? Okay, the first point is that there are a number of cavities present on the surface of a colloidal particle of enzyme. That is, a large number of cavities are present on the surface of enzyme. And these cavities possess an active group and have a characteristic shape. There are a large number of cavities are present on the enzyme surface. These cavities possess an active group and have a characteristic shape. And what will happen? Yes, there are these active centers of the surface of the enzymes are highly active. Okay, these are the highly active. The reaction of an enzyme can be compared with the mechanism of a key and lock. If we consider the case of an enzyme and a reactant, this can be compared with the case of a key and lock. That is, for a particular lock, we can use a particular key. Okay, that is, if the reactant molecules changes, the enzyme also changes. Got the point? Yes. Then what will happen? The enzyme and the reactant will react to form an activated complex. The enzyme and the reactant will react to form an activated complex. Then what will happen? The activated complex will decompose to form the products. The activated complex decomposes to form the product. If we represent E for enzyme and ES for substrate, that is reactant, then we can represent it as E plus S gives ES star. ES star means that is an activated complex. Okay, and what will happen? The ES star will decompose to form the product and the enzyme back. That is ES star gives product plus enzyme. Got the point? And this is the mechanism of an enzyme catalysis, and these are all about the enzyme. And the enzyme reaction is very important. You must study well. And later we can move to the next point, that is some catalysts used in industry. First we can take the case of Haber process. In Haber process, a finely divided iron catalyst is used. Okay, in Haber process, mainly used a finely divided iron catalyst. With the promoter is molybdenum. In Haber process, the promoter used is molybdenum and a pressure of 200 bar. In Haber process, the pressure is 200 bar and the promoter is molybdenum and having the temperature in between 727 to 773 Kelvin. Okay, and a catalyst, a mixture of iron oxide, potassium oxide, alumina are also used in Haber process. Mixture of iron oxide, potassium oxide, alumina is also used in the case of Haber process. Later we can go to the Oswald process. You know that what is the Oswald process? Yes, it is a manufacture of nitric acid. Oswald process is a manufacture of nitric acid. What is the catalyst used? Yes, platinized asbestos. Platinized asbestos is used in the as the catalyst in Oswald process and in the temperature range of 573 Kelvin. In Oswald process, the catalyst is platinized asbestos and the temperature range of 573 Kelvin. Next, contact process. What is contact process? Is manufacture of sulfuric acid. Manufacture of sulfuric acid. Here the temperature range is 673 to 723 Kelvin. In contact process, temperature range 673 to 723 Kelvin. And the catalyst used is vanadium pentoxide or platinized asbestos. Vanadium pentoxide or platinized asbestos is used as catalyst in contact process. Okay, these are mainly three important industrial preparation: Haber process ammonia, Oswald process nitric acid, and contact process sulfuric acid. Very industrial importance. So we are just discussed the catalyst and temperature range and pressure. Okay. Next we can move to the next topic, that is colloids. Okay, what is colloid? Do you have any idea? Okay, you may study it. Okay, what is colloid? Colloid is a heterogeneous system in which one substance is dispersed as very fine particles in another substance called a dispersion medium. That is, it is a heterogeneous system. Okay, it is a heterogeneous system in which one substance is dispersed. That is in the case of a solution. But it is a solution, but not at all a solution. It is different from solution. One substance is dispersed as very fine particle in another substance. That is colloids. Dispersed phase and dispersion medium. Okay, we can check why colloid is differ from solution. It is depend on the size of particle. The size of particles determine where it is a solution or it is a colloid. Okay, in solution we know that what are the particles? Yes, ions or smaller particles. Cations, anions or smaller particles. But in a colloid, the dispersed phase may consist of particles in the size of macromolecule. In a colloid, the dispersed phase may contain particles of macromolecules. In this way, the solution is changed from a colloid, or a colloid changed from a solution. Okay. Colloidal particles are larger than simple molecules. Colloidal particles are larger than simple molecules, having a diameter between 1 to 1000 nanometer. Colloidal particles have a diameter range in 1 nanometer to 1000 nanometer. Another important property, colloidal particles have an enormous surface area. Colloidal particles have an enormous, that is very large surface area. Okay, got the point? Why the solution why the solution is different from colloids? Okay. Next we can move to the classification of colloids. That is the classification of colloids. There are mainly three types of classification of colloids. The first one is based on the physical state of dispersed phase and dispersion medium. That is based on the physical state of dispersed phase and dispersion medium. Depending on the dispersed phase and dispersion medium, there are 8 colloidal systems are possible. That is, depending on solid or liquid or gas of the dispersed phase and dispersion medium, there are 8 possible colloidal systems are possible. We are just take some 2-3 examples. The first one, if the dispersed phase is solid and dispersion medium is liquid, then we get a colloidal system called a gel. We get a colloidal system of sol. Okay, that is if dispersed phase is solid and dispersion medium is liquid, we get the colloidal system of sol. S-O-L, sol. And the example of sol is paint. And on reversing, that is if the dispersed phase is liquid and dispersion medium is solid, what will happen? Dispersed phase is liquid and dispersion medium is solid. What will happen? It will give a colloidal system called gel. Okay, an example is butter. Okay, if both are liquid, displaced phase, dispersion medium, both are liquid, what is the case? It is emulsion. It is emulsion. And is very good example is milk. Got the point? So, milk is an example of emulsion, butter is an emulsion of gel, and paint is an example of salt. Got the point? If the dispersion medium is water, if the dispersion medium is water, what will happen? The salt is called aquasol or hydrosol. If the dispersion medium is water, the salt is called aquasol or hydrosol. Okay, got the point? Next we can check the classification based on the interaction. That is classification based on the interaction between dispersed phase and dispersion medium. Classification based on the interaction between dispersed phase and dispersion medium. Here the colloids are classified mainly into two categories, that is lyophilic and lyophobic. Lyophilic and lyophobic. Lyophilic means solvent attracting, liquid loving. Okay, what does it means? It is also called reversible. So we can check what is its case. Lyophilic. Here, if the dispersion medium is separated from the dispersed phase, the salt can be reconstituted by simple mixing. That is, the separation is easy and is remixing leads to the salt can be reconstituted by simply mixing with the dispersion medium. Okay, that is lyophilic case. That is, the salt, if the dispersion medium is separated from the dispersed phase, and the salt can be reconstituted by simple mixing with the dispersion medium. That is lyophilic, and these salts are called reversible salts. These salts are called reversible salts. Next is lyophobic colloids. Lyophobic, and the name meaning means liquid hating. Okay, lyophobic, liquid hating. What is it case? When the substance is simply mixed with the dispersion medium, it does not form the colloidal salt directly. Here, the colloidal salt is do not form directly. What will happen? The colloidal salt can only be prepared by special methods. Here, special methods are necessary to the preparation of lyophobic colloids. Okay, and the salt are readily precipitated and are not stable. In the case of lyophobic colloids, the salts are readily precipitated and are not stable. And these salts are also called as irreversible salts. These salts are also called as irreversible salts. Okay, this we discussed two type of classification based on the interaction and also based on the dispersion phase and dispersion medium. There is one more classification that is based on the type of particle. One more classification is remaining based on the type of particles. Okay, that we will discuss later. Today I am winding up this discussion. Study well. If you have any doubts, please clarify with the teacher. Study well, and thank you.